Thanks so much. So my name's Nick Harrigan. When I tell people I work at NVIDIA and on quantum computing, inevitably the first question I get asked is whether NVIDIA is building a QPU, whether we're building qubits. And I can start off, preempt that question. NVIDIA is not building a QPU, but NVIDIA is trying to build the systems that will be able to make qubits useful. So the systems we will need for useful quantum computing. So we are trying to build accelerated quantum supercomputers. And I will explain, hopefully, by the end of this, what I mean by that. So it's not just a new term to introduce. And so it makes sense that a company like NVIDIA would be working on a problem as important as quantum computing, arguably one of the most important computing problems we have today. But it also makes even more sense as to why we're so pivotal in this kind of field when you look at our history. So NVIDIA has a large history of enabling computing revolutions. And as we see it, those revolutions all kind of build on each other. And so to us, like quantum computing is kind of the next logical step in accelerating things with new modes of computing, and one that we think, a revolution we think is going to build on our knowledge in the previous ones. And so that's why we partner extremely broadly across the quantum ecosystem to try and build these accelerated quantum supercomputers. And so if there's one thing we're definitely in the market for, it is more partners. So if you think that we can partner with you with any of the stuff I'm going to talk about, please do reach out. We're very keen for that. This is how we're going to make this all possible. And I wanted to spend the rest of the time just quite quickly going through what I mean by everything I just introduced. So how are we trying to build an accelerated quantum supercomputer, and what does that mean? So I think it's kind of universally understood now by the community that to get to useful quantum computing, there are a few challenges. I've listed some here. I'm not going to go into any details about them specifically, but we kind of posit that all of these challenges need very powerful tools for both the development of the computers we want and for the operation of them. And that the tools that are sort of readily available to most of the researchers and developers today are not really going to cut it. So, for example, current QPUs are fantastic, and we're definitely, working on some really exciting systems. But of course, we're not quite there yet with useful quantum computing. And moreover, what we'd emphasize is that we think that those tools alone are not going to be enough to take us to the next level. So we also need really powerful simulators. And the simulators you would have available to you with just CPUs or even single GPUs are also not really powerful enough to solve the kinds of problems that simulation is going to focus on for the future of large-scale quantum computers. So things like tensor network simulations, when we start looking at large systems for error correction, dynamical simulations of hardware for like reducing the noise in qubits and understanding how to get to the thresholds we need for error correction, and lots of other things as well that might actually be relevant for introducing techniques like AI into how we develop quantum computing. And so what we think is that GPU supercomputing is going to be the key for enabling large-scale quantum computing, and for a number of ways. So as I just mentioned, GPU accelerated simulations will be key. We're very active in AI for quantum computing, something that Mark mentioned at the start of the session. So finding out how AI techniques are going to be helpful, not just in simulation and algorithm development, but also in actually running a quantum computer. So things like decoding, AI decoders and calibration techniques. And then also the actual supercomputing infrastructure you need to put a QPU into to run it. So we are doing a lot of work to try and understand how like GPU acceleration and AI techniques are going to be useful for those operational tasks. So again, decoding, calibration, measurement readout, those kinds of things. And so that's what we're doing. So we're working with a lot of centers of excellence, high performance computing centers across the world. I've just called out two here, IIST in Japan and Gefion in Denmark. And we're enabling them, we're giving them the tools, the GPU supercomputers, so that researchers can build, well, the whole quantum research ecosystems are building around these devices because they let people study the kinds of things they need to get to the next level. And we're also working with partners, some of which people have already talked about this, taking QPUs into supercomputing centers and experimenting with actually connecting those devices together to allow hybrid algorithms, to allow hybrid quantum classical computing. And we have a product line that kind of supports this. So overarching in our product line is QED-C, which is our accelerated quantum supercomputing platform. And this is a software product that is built very much from the ground up for hybrid quantum classical computing. And so this is something that you can plug in as a backend, a simulator. So we have Quantum, which is like the fastest GPU accelerated simulator there is for state vector and tensor network simulations, but also it's completely hardware QPU agnostic. So you can plug in one of any of a large number of QPU backends to this. And moreover, when you're thinking about the reality of actually performing quantum algorithms where you need access to both GPUs, QPUs, and CPUs, we also have CUDA-X as a backend, which has got the world's fastest implementations of many of the algorithms and tools you will need for the classical side of those hybrid algorithms. And so that's kind of where I wanted to wrap up. I'm obviously happy to talk much more about this in the discussion, but I've had some links there for you to find out more about what we're doing. And thank you very much for your time.